Hi, good evening students. I am going to explain to you the force acting on a current carrying conductor. Look at the picture. Understand the picture first. Can you all see a horseshoe magnet? The bottom pole is the north pole and the top pole is the south pole. So the magnetic field lines start from the north pole and end in the south pole. So there will be a magnetic field in the upward direction like this. So this is the direction of the magnetic field. Understand? The direction of the magnetic field is in the upward direction. And in the space between the two poles, you can see XY is an aluminium rod. XY is an aluminium rod which is suspended by two wires, two conducting wires. And these two wires, you see that the two end points of the wires, they are suspended from a iron stand. So this is a iron stand held vertically from this horizontal rod. From this horizontal rod, two wires, okay, are balancing the aluminium rod XY, and the two wires are extending up to the battery. Okay, the two wires are extending up to the battery. So this end X, you can see that left end of the aluminium rod, namely X, is connected with the help of a wire, and it is connected to the positive terminal of a battery. And the end Y, you can see here, this is connected to the negative terminal of the battery in series with a plug key. Okay. Suppose if I will close the key, means the conventional current will start from the positive terminal of the battery. So the current, this is the current, okay. I is the current which is flowing through the circuit, okay. First it enters the end X of the aluminium rod, then the current is flowing from X to Y. Can you see this is the direction of the electric current, okay. Suppose if you take this aluminium rod, means the aluminium rod is now perpendicular to the plane of the board. So if this is the board, means the aluminum rod is suspended perpendicular to the plane of the board, and you can imagine the horseshoe magnet is held like this. Okay, this is the position of the horseshoe magnet, and my thumb is the north pole and this forefinger is what, the south pole. So what is the direction of the magnetic field is from the thumb upwards to the forefinger, okay. And the aluminium rod is held perpendicular, okay, perpendicular to the board and also perpendicular to the magnetic field. And the current is leaving the aluminium rod at the point Y, okay, and the circuit is getting closed at the negative terminal. So it is a closed circuit inside which current is flowing. The moment key is closed, the current will flow through the conductor from X towards Y. And instantaneously, what was observed means this rod XY was moving towards the right hand side. It was moving towards the right hand side. It was deflected. The entire rod was pushed towards the right side. Why? Because that rod XY is experiencing a mechanical force. And this mechanical force experienced by this rod is also called as the motor force. Motor force. Then it was found that when the battery connections or terminals are reversed such that is Y is connected to the positive and X is connected to the negative. Only the battery terminals are interchanged, so that this time the current is going to flow in the reverse direction. Earlier the current was flowing from the end X to the Y, okay. And suppose if you change the battery terminals, means this time the current will flow from the end Y towards X. In such a situation, what was observed means the rod was deflected in the left hand side. Okay, when the battery terminals were interchanged, means the force was changing its direction. But in both the cases, only one very interesting thing was realized. That is some relationship between the direction of the current, the direction of the magnetic field, and the direction of the mechanical force or the motor force acting on the aluminium rod. Okay. So once again, very quickly I will tell you. First, what we did, the current was allowed to flow through the aluminium rod in which direction? From X towards Y, that is into the board, perpendicular to the magnetic field. And at that time the force, say for example it was F1 in the first case. So it was along the right hand side. The rod was pushed towards the right side with the mechanical force. Next time what we did, we interchanged the battery terminals such that X, the end X is connected to the negative and Y is connected to the positive. Now the current is flowing from the end Y towards X, that is from the board towards U, pointing towards U. So in this case also current is perpendicular to the magnetic field. But this time that aluminium rod was pushed towards the right side with some force F2 in this case, okay. So that in both the cases there is some relationship between the direction of the current, direction of magnetic field and the direction of the mechanical force or the motor force, okay. Now you see the first case. In the first case, see, when the battery terminals were originally connected, the direction of the magnetic field was upwards from the north to south, okay, north to south, and direction of current, the conventional current I is into the board, that is from X to Y, okay, and direction of the motor force F, that is towards the right. This is the first case. Now what is the relationship between the directions of the current, magnetic field and the force? No, it was given by a rule which was called as Fleming's left hand rule, okay. This is a rule called Fleming's left hand rule, and this rule is used to remember the relationship between the three directions what I told now, okay. So what is the statement of the Fleming's left hand rule? Now if you take your left hand, okay, first I will stretch the thumb alone. Then I will stretch the forefinger like this, such that these two are perpendicular to each other. Then slowly I will bring the third, that is the middle finger also, such that these three fingers are mutually perpendicular to each other. Okay, so these two are already perpendicular to each other, and these two are perpendicular to each other. Therefore, these two fingers are perpendicular to the thumb. So all the three fingers are now mutually perpendicular to each other. You can also try like this. How means, first stretch the left hand, okay, such that the thumb is stretched upwards and the forefinger is held perpendicular to the thumb. Third, the middle finger, okay. So I will write first, so stretch the thumb. Then what finger I told you? This finger is called as what? Forefinger or index finger. Better we will write what? Forefinger, okay. And the middle finger, okay. Of which hand? That is very important. Of the left hand, okay. Of the left hand. So this is the thumb, okay, forefinger and middle finger of the left hand, such that they are perpendicular to each other, okay. They are mutually perpendicular to each other, okay. Now what do we want to say is, I have stretched the three fingers such that they are mutually perpendicular to each other. Now the middle finger indicates, okay, middle finger indicates some quantity. What is that? The middle finger gives the direction of current, and the forefinger indicates the direction of magnetic field, okay, direction of magnetic field. And what is the leftover finger? Is the thumb, okay. So the thumb indicates the direction of motor force, direction of mechanical force or motor force, okay. So all the three directions are related with the help of the three fingers of our left hand. So what is the statement of Fleming's left hand rule? Stretch the thumb, forefinger and middle finger such that they are mutually perpendicular to each other. If the middle finger indicates the direction of what? Current flowing through the conductor, then the forefinger indicates what? The direction of the magnetic field, so that the thumb indicates the direction of motor force. So another way also is there. In many ways this can be interpreted. Okay. So the middle finger can also be called as a central finger. Central finger. So out of the 5 fingers, this is at the center. So center starts with the C. Current also starts with the C. Forefinger starts with F. Field also starts with F. So this is the clue. Okay. So that you can remember these two. So that automatically the thumb indicates the leftover. That is the motor force. Okay, students. So now in this picture, once again you see that initially the end X is connected to the positive terminal and Y is connected to the negative terminal of the battery, such that the current is flowing from X to Y. In which direction means it is flowing into the board. It is flowing into the board. And which finger explains or gives the direction of the current is the middle finger. Okay, middle finger. So middle finger means what? It is into the board. And which finger gives the direction of magnetic field in the upward direction is the forefinger. Okay. So you see that, okay. So this is the middle finger, this is the forefinger. So the forefinger is upward. Can you all see? See the board. From the north to the south, this is the forefinger. You have to keep like this. And when the current is flowing into the board means the middle finger, you see that it is kept inside. You see here, it is kept inside like this. Okay. So this is perpendicular to each other. Now look at my thumb. In which direction? It is pointing towards me. Okay, with respect to the board, it is pointing towards the right hand side. Okay, are you understanding? Like that, now you can see that the force is acting towards the right. Okay, so in this case, the 3 vectors are perpendicular to each other. The 3 directions are mutually perpendicular to each other. So this is a simple experiment or activity to understand that when a current carrying conductor is placed inside a magnetic field, it will experience a force. That is very important. This is very, very important. So current carrying conductor, a current carrying conductor, okay, placed inside a magnetic field, experiences a motor force, mechanical force, okay, experiences a mechanical force which is called as the motor force. This is very, very important, and this is also called the principle of working of an electric motor, which is the next topic. Okay. So what happens when a current carrying conductor is placed inside a magnetic field means it will experience the force. Now what is the reason why it should experience the force? I will tell you in a nutshell. Now you see here, when current is flowing from the direction X to Y, when current I, conventional current is flowing, in which direction do the free electrons of the conductor flow? Opposite to that of the conventional current, is it not? So the free electrons present inside the conductor will flow from the end Y up to the end X. So already I have told you that in a current carrying wire, as Oersted has observed, why there should be a magnetic field surrounding a current carrying conductor. When charges will move from one point to another point, means moving charges will produce a current, and this current will produce a magnetic field along circular path, concentric circles around the straight conductor. So since the conductor is straight and inside the conductor electrons are flowing from one end to the other end, magnetic field will be produced in circular loops. And this magnetic field produced by the current carrying conductor is interacting with the magnetic field of the horseshoe magnet. Again I told you, one magnetic field can interact with another magnetic field. So the weaker field only will be deflected by the stronger field. Here the horseshoe magnet is having a permanent magnetic field which is stronger than the magnetic field of the conductor. Also conductor is freely suspended so that it can move easily. That is why here conductor. Imagine if the magnetic field produced by the conductor suspended is very much stronger, what will happen? Horseshoe magnet also can be deflected, isn't it? But here it does not happen because horseshoe magnet is very strong and it is fixed, and the aluminum rod is thin and it is only deflected. So remember, my dear students, when a current carrying conductor is placed inside a magnetic field means it experiences the mechanical force. Now one small question I am going to ask to you. instead of this current carrying conductor, okay, you take a single electron, only a single electron having a negative charge is moving, okay, is moving now perpendicular to the magnetic field. Will it experience a force or not? It will also experience a deflecting force. It will also experience a motor force. I will tell you how. See here, for example, now let us consider a uniform magnetic field, okay. So this is a uniform magnetic field B. B is the symbol, no? B is the symbol for what? Magnetic field, and uniform magnetic field is represented by horizontal and parallel lines. So that the magnetic field strength is constant everywhere. In such a magnetic field, let us take an electron. An electron is moving perpendicular, okay? An electron is moving perpendicular. So this is an electron, okay? That is the direction of motion of the electron. When the electron is moving in the downward direction perpendicular to the magnetic field, means it will experience the motor force. In which direction the force will act? Now you guess and tell me. Okay? Yes, the electron is what? Negative charge. But actually in this statement, Fleming's left hand rule, this middle finger gives what? A direction of the current. What do you mean by current? Conventional current means what? Positive charge. But electron is what? A negative charge. When negative charges are flowing in the vertically downward direction, in which direction should the conventional current flow then? In the upward direction. Here only you have to think and answer such questions, okay. So now I will take, though the electrons are flowing in the vertically downward direction, the conventional current, okay, convention current or conventional current is flowing which direction? It is flowing in the upward direction. Again you stretch your left hand. Current means what? Which finger? It is denoted by the middle finger. Okay, already this magnetic field in which direction? That is towards the right, okay. So now you can stretch, the finger like this, okay. You see that forefinger gives the direction of magnetic field B, okay. And you see that current, conventional current is flowing in which direction? Upward. You see my finger, okay. So that where is my thumb? You see, thumb is going into the board. Is it not? So the force, the deflecting force is what? Acting inwards into the plane of the board or into the plane of the paper. So in this case, the force, okay, the force acts, okay, into the board. Force acts into the board, or the, if it is paper means inside into the plane of the paper. Okay, my dear students, so totally what you have to remember from this activity is, whenever a current carrying conductor is placed inside a magnetic field, okay, it experiences a deflecting force or mechanical force, and this force is called as a motor force, and there is a relationship between the direction of current flowing through the conductor, magnetic field, and the motor force, okay. And that relationship is given by which rule? Fleming's left hand rule. What is the statement? You stretch the left hand such that the thumb, forefinger and middle finger are mutually perpendicular to each other, okay. Now the middle finger indicates the direction of current flowing through the conductor. The forefinger indicates what? The direction of the magnetic field. And the thumb indicates what? The direction of the motor force or mechanical force acting on the conductor, or direction of motion of the conductor. Hope you should have understood. Okay, now the next topic is electric motor. Okay, wait. Electric motor. It is a device which converts electrical energy into mechanical energy. For example, let us take a ceiling fan. When we switch on the fan, it rotates. How is it possible? When we switch on, the electric current is flowing through a coil which is kept between two magnets inside a motor which is located inside the fan. So the motor converts the electrical energy supplied to it into mechanical force or mechanical energy. So the blades which are fitted to the motor will be rotating fast with some mechanical energy. So this is why motor is a device which is converting which energy into which energy? Electrical energy into mechanical energy. Now, on what principle does this electric motor work? A current carrying conductor placed inside a magnetic field experiences a mechanical force, and the direction of this force is given by which rule? Fleming's left hand rule. But in the CBSE exam, board exam or any other examination, what is the principle of electric motor means? Still most students are confusing themselves. Some are writing that principle means the conversion of electrical energy into mechanical energy. Some are writing Fleming's left hand rule is the principle of working of motor. But actually what is the expected answer? I will tell you, my dear students. You may write that motor converts electrical energy into mechanical energy also. But what is the actual principle is when a current carrying conductor is placed inside a magnetic field, it will experience a mechanical force. If you want, additionally you can write that the direction of the force is given by Fleming's left hand rule. Okay, now look at the first diagram alone. Okay, the first diagram. Here A, B, C, D is a rectangular coil. That is, a long wire, insulated copper wire is taken and it is wound in the form of a rectangle, bent in the form of a rectangle. Here only one loop is shown. Actually in the motors used in fan, mixer, grinders, in all other equipments and all, heavy coils will be wound over a soft iron ferromagnetic material. That in the later stage only you are going to study in higher classes. But now how many windings are there for the coil is only one loop, okay, one rectangular loop A, B, C, D. And the two end points of the coil are A and D. The end A is connected to a half circular metallic ring. It is in the shape of a half circle that is denoted by P. And this ring is called as a split ring. A circular ring is taken, it is split into two halves. Those two halves are called as split rings. And this is P, which is connected to the end A. And the other end of the coil, namely D, is connected to another split ring Q. So P and Q are the split rings. And this coil is placed inside the magnetic field, okay, of two bar magnets, or a single horseshoe magnet also can be used. So the magnetic field is provided by this N and S. Then you can see that the two split rings P and Q, they are movable, they are fixed with the coil. So whenever the coil is going to rotate, along with the coil, who is also going to rotate are the two rings, namely P and Q. Because the coil is fixed to an axle, whenever the coil rotates, the two rings P and Q also will be rotating along with the coil. Then you can see the two more portions, rectangular blocks, okay, that is X and Y. They are made up of soft metal like a carbon or soft metal, understand? And they are permanently fixed. They are not going to rotate. They are not going to rotate. They are stationary. Okay, they are made up of carbon. And whenever the coil is rotating, along with the coil, the two rings, namely P and Q, the split rings P and Q also will rotate. And whenever the rings rotate, they will brush against the carbon blocks X and Y. That is why the portion X and Y are called as brushes. They are fixed, they are not moving. And then the wires are connected to X and Y. The end X is connected to the positive of a battery and the end Y is connected to the negative of a battery in series with the plug key. Okay. Now what are the essential parts? Once again let us make a list. So what are the essential parts of an electric motor? First essential part is the coil A, B, C, D. It is rectangular in shape. In this picture it is having only one loop or one turn. But in the actual heavy motors and all, many number of loops will be there, okay? And they are wound over a ferromagnetic material like a soft iron. And that is also getting a name as armature coil. In the other higher order applications, it is getting the name as what? Armature, okay? Next, second one. The second essential part is what? The field magnets, N and S. I told you it may be supplied by 2 bar magnets or a single horseshoe magnet also can be chosen. And the third essential part is the split rings P and Q. I told you they are semicircular rings and they are connected to the 2 free ends of the coil. Whenever the coil rotates, the 2 split rings P and Q also will be rotating. Understand that? The fourth essential part is the carbon brushes, namely X and Y. These X and Y are fixed. They are fixed. They are stationary. They are not going to move. They are connected to the battery and the plug key. So they should not move. Okay, students, now shall we see the working of the motor? Okay. So, working of a motor. So regarding the working of motor, it is better always we draw 2 diagrams. Okay. So I have drawn another diagram also. I will explain how to understand from the first diagram and second diagram separately. Now look at the first diagram once again. I am going to close the key. When the key is closed, conventional current will start from the end positive terminal of the battery and it will enter through the carbon brush X through the ring P and the current is now flowing in the coil. You see continuously the path of the current you will have to follow. The current in the coil is flowing from the end A towards B, then B to C, then C to D and then D to the ring Q, then Q is in contact with Y and again it is flowing towards the negative of the battery. Is it a closed circuit or not? The current is completing one closed path. Now what is going to happen? The conducting portion, that is A, B, C, D is made up of conducting wire. It is placed inside a magnetic field. The moment current will flow through the conductor. What is going to happen when a conductor carrying current is placed inside a magnetic field means it will experience a force. Is it not? Now you see that now the direction of the magnetic field. The direction of the magnetic field is from the North Pole to the South Pole like this. So from the North Pole to the South Pole there is a magnetic field. And inside the magnetic field, now current carrying conductor AB and current carrying conductor CD are kept perpendicular to the magnetic field. So they will experience a maximum force. Understand? They are going to experience what? A maximum deflecting force or maximum mechanical force. So what will happen? The force acting on AB will push that in the forward direction. So that it will AB will move in the downward direction forward. At the same time, CD will also experience a force which is going to push CD in the upward direction. And this force experienced by the portion AB and CD can be understood by using Fleming's left hand rule. Just now I have explained to you Fleming's left hand rule. Which 3 fingers of the left hand should be stretched is what? The thumb, forefinger and the middle finger. Now along with me, you also be ready. You stretch your left hand and now you look at the direction of the magnetic field. Is it upward or downward? Okay, downward direction. Which finger is giving the information about the direction of magnetic field is the forefinger. Downward means forefinger is like this. Understand? Okay, now the current is flowing from A to B. In which direction? From A to B in the left hand side, in the left hand direction. Is it not? So like that you can see. Okay. So the current is flowing from A to B, and now you see that the magnetic field like this. If you keep it, it will be better. I think you see here. You just see here A to B. Okay. A to B is the middle finger and N to S is the forefinger. Okay, they are perpendicular to each other. Now the thumb is pointing towards you. It is perpendicular to the plane of the board in the forward direction. So that what will happen? This portion AB will be rotating downward direction. It will be falling in the downward direction. As a result, now CD has to go up. Is it not? The same Fleming's left hand rule you apply for CD. Now current is flowing in which direction? C to D. Is it not? C to D like this. Okay. So the current is flowing C to D. Now you see that the magnetic field is like this. Okay, magnetic field is in the downward direction, the current is flowing from C to D, and the thumb is pointing into the board. So for the current carrying portion AB, the force was acting towards you, and because of that AB is falling down, and here CD, the force is acting into the board, therefore no, it will be moving in the upward direction. So here current flows from the direction, that is A to B, and as a result the force, okay, the force I will take here on the force, okay, as a result the force acts on AB. So the portion AB comes down, and the portion CD goes up. Okay, CD goes up. So current flows in the direction A to B on the top, and the bottom it is flowing from what, C to D. As a result, what happens? Two forces are acting on the portion AB and CD. The force acting on the portion AB will bring AB downward, and the force acting on CD will push CD upward. As a result, what will happen? These two rings are also connected to the coil. So whenever the coil is rotating, these two rings P and Q also will rotate. So this is going to happen during the first half rotation. So what will happen? This P also will be, that is a ring P. Okay, this will come down. This comes down. And the ring Q, okay, the ring Q is going up. So this goes up. So that when earlier P was in contact with X, after half rotation is over, now P will come in contact with Y. Similarly, earlier Q is in contact with Y, means after half rotation is over, what Q will go in contact with X. So that now the coil position will change. This end will be D, this end will be C, and this end will be B, and this end will be A. And here Q will come in contact with X, and the ring P will come in contact with the Y. Completely the position of the coil and the two split rings will change. Is it not? So now how many rotations are over? Means half rotation only is over. Only half rotation the coil has completed. So this happens during the first half rotation. So the working of the coil. So this happens during the first half rotation only. Now during the second half rotation, what is going to happen? Let us see now. You look at the picture once again. The conventional current, the moment I close the key, means what will happen? The current will flow from this positive terminal, and now the current enters the coil in which direction? D to C, and C to B, then B to A, and then towards P. Now the same Fleming's left hand rule, once again if you use, means what will happen? A force will act on the portion CD in the forward direction, perpendicular to the board towards you, so that CD will come down. So this time what will happen? CD, okay, comes down, and the portion AB goes up. Okay, like that. So during this, once again what will happen? Again P will be brushing against Y, and then it will go in contact with X, and Q will come in contact with the Y. So like that ring, okay, ring P will go up. Okay, ring P goes up, and ring Q comes down. Okay, ring Q comes down. So this is happening during the second half rotation. After two half cycles are over, that means one full rotation is completed, the position of the coil will come back to the first picture. Okay, so the coil position is what? A, B, C, D. Now during every half rotation of the coil, forces will be acting on the portions A, B and C, D. The force acting on the portion A, B and C, D during every half rotation will be equal in magnitude but opposite in direction and parallel to each other. Such a pair of equal and opposite forces which are parallel to each other is called as a couple. Couple means a pair. So what is the effect of the couple acting on this coil? What effect this pair of forces will produce is called as the rotational effect. That is called torque. In higher studies you will be learning more about it, torque. And as a result of the torque acting on the coil, it is rotating in the anti-clockwise direction. You can see the direction of rotation of the axle. So the axle and the coil and the two rings P and Q, okay, together, they are all fixed together. They continuously rotate in the forward direction, that is the anti-clockwise direction. Now one more observation is, the current always is supplied by the positive of the battery, okay. Conventional current in both the half cycles, you see that the current is sent in the same direction. Such a current which is flowing in the same direction, okay, that is called as a direct current, DC. Direct current means the current which is flowing always in the single direction or the same direction is called the DC, okay. And when the current is flowing inside the armature coil, in the first half cycle it is flowing in the direction A, B, C, D. In the second half direction it is flowing in the direction D, C, B, A. So for every half rotation of the coil, the current direction is changing, and this direction change of the current is happening because of the rotation of the two split rings, namely P and Q, okay. So during the first half cycle, okay, during the first half rotation of the coil, in which direction current is flowing? Current is flowing in the direction A, B, C, D. Now during the second half rotation, okay, the current is flowing in which direction? It is what you look at the picture, DCBA. So the current is flowing in the direction DCBA. And who is responsible for the change in direction of the current is the pair of split rings. So these split rings only are responsible for the change in direction of the current P, Q. This arrangement is called as commutator, okay. This arrangement is called as commutator. So what is a commutator in general? Commutator is a device which is used to change the direction of current during every half rotation. And since the split rings P and Q are changing the direction of the current, here what is the role of the split rings in the DC motor? It plays the role of a commutator. Understand? Okay students, I hope you must have understood. So what is an electric motor we have studied? It is a device which is used to convert electrical energy into mechanical energy. And what is the principle of working of a DC motor? Yes, when a current carrying conductor is placed inside a magnetic field, it experiences a force, okay. And the direction of this force is given by which rule? Fleming's left hand rule. So what is the application of these motors in general? Okay, in general motors are used in what? Electric fans, mixers and grinders. So in commercial motors like the mixers, grinders and fans and all, the coil consists of several number of turns and they are wound over a soft iron core. Okay, number of turns also will be more. Okay students, let us meet in the next topic. Until then, bye.